Hello, welcome everybody. My name is Alberto Marquez, and in this video we're going to discuss how to use Excel to compute control charts and also how to go about computing Cp and Cpk. Let's just jump into the data using Excel. Very good. Here we are in Excel. What we have is sample sizes, a sample size of 6, and we have 42 samples. And if we wanted to construct a control chart for variables x, and the simplest one is to use the control chart for the range, what we would need to do is first of all compute precisely the mean for x bar and the range. So that's what we're going to do. The computation is very simple. In Excel we have the formula average, and we do that for each one of the readings. It's very easy to compute this formula down for all the data that we have just by double clicking in the corner, and it is automatically copied for all the 42 data points that we're going to be using. So this is going to be our x bar as meaning the mean, and then the range we can compute also using Excel. Has, let me see, well, we can use the maximum minus the minimum. I thought there was a function for that, but I didn't see it right away. But it is not a problem. I can do maximum minus the minimum, and that will compute the range. So now I have that computed. It's important for me to have the central line for both the x bar and the range, and that will be the average of these two columns. So I will compute the average of the averages. And again, I'm using the arrow and end shift and that sort of options to copy faster. Let me do it in slow motion. Here we have equals, and then I have average, open the parentheses, and when with the arrow I go to the start of the column, then I press shift, end, and arrow down, and that takes me to the end of the data. I close the parentheses and hit enter, and that's very fast. You don't have to scroll down using the mouse. So this is the x double bar, if you will, the average of x bar and the average of the range. From this moment, what we need to do is we need to use the values in the tables. So let's consult the formulas that we have. These are the formulas that you can find in the Blackboard page, and what you will find is that we have the control limits x bar chart and the control limits for R chart to be using the factors A2 and D4 and D3. So we're going to get those from the book, and also you have them here at the bottom of the formula sheet. So since we have sample sizes of 6, A2 is 0.483, D3 is 0, and D4 is 2.04. So those are the values that we're going to use. So let's go back to Excel. So here we are with Excel, and as we said, the average was 99.85, the A2 is 4.83, and in order for us to compute the upper and lower limit of x, the upper control limit of x bar is the average 99.85, making the absolute reference, plus A2 times the range, and that's our best estimate for where we should have the upper control limit. And this number is going to be the same for all the graphic. We can compute now the lower control limit for x bar and the only difference is that we're going to subtract now the effect of the range. So this is going to be the mean minus a2 for n equals 6, all that times the range. And you see the only difference is that we're now subtracting. And format this, and for purposes of computing the range graph, what we can do is we can bring this separately. We can bring all these together, because now all of these can belong into the same graph. Let's include here the numbers 1 through 42, and well, it's not n, it's actually the sample number. But let's we can insert the graph now. Insert, and then I think we can use, there you go, and that would be your control chart. This will be your control chart, the corner. This will be your control chart for X. And that should work. There you go. And all the points are within the limits. If any of the points would be out of the limits, we would need to eliminate that point and recompute the limits again. But that didn't happen, so we have the values for what would be the control chart process series. Now that's for the mean. We need to also have a control chart for the bit to the side. Now, for purposes of the upper control limit for R, what we do is we multiply the average R times, because we're going to repeat that same computation for all the rows, and that times d4, and the lower control limit for R bar is the range times d3. In this case it's just 0. There it is. That's a computation we can do now. Copying this down, add the number of the sample, sequential number, and then we can insert our graph. And this is our control chart for R, and that looks pretty good. Everything is in control, and we have computed the control chart. Alright, let's work now with the computations of Cp and Cpk. In order to do that, we need to know what are the specifications, and then we're going to compare the performance of the process against that specification. So what we're going to do first is define that. Let's say that we expect to have the process from the specification perspective to be centered, and centered in this case looks like, well, it doesn't depend on what it looks like, it depends on what it should be from the engineering perspective, but let's say that we expect this to be centered at 100. Also, let's assume that the specification tells us that it could be plus minus 4, right? So this would be 100 plus minus 4, plus minus 4. That means that the limits that we could have for the process to be within the specs at would be the upper limit for the spec, upper spec limit would be 104, and the lower spec limit would be 96. So anything that falls beyond that region, we would have to assume that it's not compliant. Oops, I should have done. Very good. So I'm going to move these specifications here on top so I can work here at the right hand side. So I need to identify which one of these data points falls out of a specification, and it will be very slow if I have to do this by sight, and it will be prone to errors and things like that. So I have it in Excel. I can use the facilities I have in Excel. So what I'm going to do is I am going to ask if, and then I'm going to identify this as a defective product if it's below the lower limit or above the upper limit. So it's going to be an OR condition. If this particular value is larger than the upper control limit, or if that same value is smaller than the lower limit, one or the other. If any one of those two happen, then I'm going to count it as a defect, and I just place 1 to count it. Otherwise, it's not going to be a defect, and it doesn't matter if what the number is, because it's within the specs. And that's all I have to do. It's asking me to close properly the parentheses, so I need to go back here, and I open a parenthesis for the OR condition, so I need to close that parenthesis on the OR condition, and then I have the value for when it's true and the value for when it's false. So for the first one, falls within the range, and it's not a defect, it's not beyond the specs. So all I have to do now is copy that formula. Notice that when I use the formulas, I use these dollar signs for absolute value. I toggle that using F4. You can do that pressing F4 in your keyboard to make it faster. And then all I have to do is copy that formula to the right and then copy that formula down. Okay, it's 42 rows. So there are some instances in which we don't have any defects, which is good, but in sometimes we have more than one. So now we can know which one of these are out of specification, right? So that allows us to compute a percentage of product that it's appearing to be out of specs. How do we do that? Well, we can add all the ones, and that tells us how many are out of spec. And I can, oops, I'll do that again. We can add. Okay, so we can compute the percentage of the effective product in this sample by adding the number of the effective product, 61, and then we divide by the total number of products. We can just count the number of data points. We have 252 points, and the percentage of the effective is 61 divided by 252. It's 24%, a very large number. That is not complying the specs. If our specs would be 104.96. Very good. Now, in order to compute the Cp and Cpk, we will need to know what is the standard deviation, because the Cp depends on the computation of plus minus 6 sigma, and in order to do that, we can compute. We're going to need both the mean when we compute Cpk and the standard deviation for both Cp and Cpk. Standard deviation. So we know that in Excel we have average. We compute the average of all these data points, 99.85. Standard deviation equals standard deviation. We select the points. We have 2.99. So based on the formulas for Cp and Cpk, let's review that. Here you have them from the formula sheet. The Cp is the upper specification limit minus the lower specification limit divided by 6 sigma. So let's compute Cp. So Cp is equal to the upper specification limit 104 minus the lower specification limit 96. All that divided by 6 times. The number that we have is 0.44, and this translates to the fact that in order for us to have only about 0.26 or 0.27% of defects, that is at 3 sigma on each side, we would need to have a Cp of 1. We don't have a Cp of 1, we have a Cp of only 0.44, and that means that we're going to be having problems with a lot of product that is out of specification, and that is reflected in the 24% that we computed before. Now the Cpk is more stringent, because what it does, let's review the formula. The Cpk is the minimum between the Cp in the upper side and the Cp on the lower side. The Cp on the upper side makes the computation of the upper specification limit minus the mu minus the average divided by 3 sigma, and CPL computes the mean minus the lower specification limit, all that divided by 3 sigma, and then CPK computes the minimum of those two. So it is going to where it's even more unbalanced and where most of the error will come, although with our CP of only 0.44 we may be having problems on both ends. So let's go. So before we compute the CPK, we're going to compute just CPU, which is not stands for the central process unit. Is the CP, the capability of the process on the upper side. So this is the upper control limit minus the mean, divide that by 3 times the standard deviation of our process, and the number that we have is 0.46, and that is larger than 0.44, so the central the capacity of the process in the lower side is going to be smaller than that, because the CP is at the center between the CPE. So we're going to compute now the mean, and this is the mean minus the lower specification limit, all that divided by 3 times sigma, and I have that number. With that many digits, it may be difficult to read, so I'm going to standardize it, let's say 3 digits. So the CPK will be the minimum of these two, it's a formula, and the CPK is 0.429, which is a very low number. We need it to be around 1, and that means that we're going to have a lot of problems in satisfying the requirements for the specs. That's why in quality what we want to do is to reduce the variability, because if we were to reduce the variability, let's say now that right now the standard deviation is 2.99, but let's say that you manage to reduce that variability to only 1, then all of a sudden our CPs and CPKs are above 1, which is everything is working smoothly and everything is good. So that's why it's so important to have the standard deviation reduced. Alright, so this is this video, and I'll see you in the next one.